Okay. All right. So now I can run it. Oops. Okay, so one way to do it is we can have a mathematical proof for coming up with approximation ratio. So that's what we are going to do in this video. So we're going to see two NP-hard problems, and then we're going to see how we can come up with an approximation algorithm and prove approximation ratios. The other approach will just be coming up with an approximation algorithm, which often not so hard. You just come up with a greedy choice, right? And then you don't know how to prove mathematically a approximation ratio. So then what people do is, okay, so we run numerical analysis on certain inputs of moderate size. You can come up with an optimal solutions, and then you compare your optimal solutions with approximation solutions. And then you draw a line graph, and then you see how close it is. Okay, so that means that running numerical analysis and coming up with optimal solutions may take, sometimes it may take days, or sometimes it may take weeks of computation time, depending how large your data sets are. Because they are NP-hard, you don't have polynomial time algorithms for doing that. So, so these two approaches have been used in research, but for us, because we are in algorithm class, so we are more interested in this approach. So how can we come up with a proven approximation ratio for the algorithms we design? Okay, but this is not always possible. Okay, so we need to make that clear. So it is not always possible to come up with a proven approximation ratio. So so this I mentioned these two approaches. Then next we're going to see how what it means by an approximation ratio. As I said earlier, we did see it when we talk about independence sets. Okay, so but now let's see it again. So suppose that the cost, okay, so each optimization solution has a cost. You come up with a cost. So that optimal solution cost is a C star, which we don't know how to get it, but we can do mathematically and compare it, right? And the cost of an approximation, so which we know because we have an algorithm, we have an approximation algorithm, we can produce this C. But we just don't know how to do this, except you run numerical analysis on moderate inputs. Okay, so then we say that the approximation algorithm has a ratio rho of n if for any instance of size n, okay, the maximum of C star over C and C over C star is bounded above by rho of n. So if, for instance, for optimal solution, we have a maximization or minimization. So if it's a maximization, then you use this because your C cannot be greater than C star because C star is already optimal, that's already maximum. If your optimal solution is a minimization, you use this because your C cannot be smaller than C star, right? So C will be greater than or equal to, well, the best of course is C is equal to C star, but in general it's greater than C star. So you compare these two, their value will always be greater than or equal to 1. So what we are interested in here is the upper bound. So if this upper bound is a constant, then it will be good, right? Because so that means that our approximation algorithm is off by a factor, a constant factor of the optimal solution. Okay, so that's what this means. All right, so now let's move on to see some examples. Okay, so the first example we're going to look at is called vertex cover problem, and then we move on to TSP. So vertex cover is NP-hard, which is to find on a given undirected graph G, the minimum subset of nodes V prime, which is included in V, such that for any edge UV, if you take the endpoints of UV, then one of the points is in V prime. So then this is called vertex cover. So in other words, it covers every edge. So one of the points will be the endpoint of every edge, right? So let's say you have, this is your V, and of course you have a subset of V prime, and then for any edge in G, either U is in V prime or V is in V prime or both, right? So it just means that you take these endpoints, these endpoints intercept V prime is not empty. So which means either U is in it or V is in it or both are in it. So what we are interested in here is to find a minimum node cover or minimum vertex cover. So what would be the smallest V prime that covers all the edges? For instance, if you have a star network, and the minimum one, of course, it's just the minimum vertex cover is just one. I just use the center points. So that covers every edge, right? So, but in general, this is what we are interested in. We want to find a minimum subset that covers every edge. So the decision version, okay, so the decision version of VC will be you get a G and then you get a K. So then you find a subset of V prime such that the size of a V prime is at most K. Okay, so similar to the TSP, so at most K. And then if that decision version is solvable in polynomial time, then you can do a binary search on this K to come up with a polynomial time algorithm for VC, for this the minimum vertex cover. But the decision version of VC is NP complete. Hence, this is NP hard. So that means we don't have a realistic hope to find a polynomial time algorithm. So what do we do? Well, we find an approximation. Okay, so the approximation here is pretty straightforward. So let me start a whiteboard. Okay, so let's say I have a G given. So I just think of, okay, this is my G. So what do? I pick any edge, select any edge U, V, in E. Okay, so then I will place my U and V into my set V, the subset of V prime. So I'm going to place, initially V prime is empty, right? So we can say initially this is empty. We can place U and V in it. So you just pick any edge and then remove any other edge that's incident to this edge. remove them. So these are removed, including this. So then you have the remaining subgraph. After all these edges are removed, then I repeat the same thing. I pick any edge in the remaining graph. And then we remove anything that's incident to this edge. And then you keep on doing until I don't have any edge left. So that's how I'm going to compute this V prime. So I get a vertex cover because it covers every edge. So the thing is that how good is this vertex cover compared to the optimal solution? Okay, so that's so the optimal solution. Maybe I can put it here. So you can see a so we can let an optimal solution V star be an optimal or minimal, in this case, a minimal vertex cover. Okay, then you look at, so this means that every edge has a end node that's in V star. Okay, so now what we are going to see here is that I want to know the relation, the size of V star and the size of V prime. Now V prime is I constructed, and V star I don't know, but I know what it means, right? It is the minimum vertex cover. Okay, so now let's see the proof. Let's move back to my slides. All right. All right. Okay. So now we let E prime be the set of edges. Okay, actually it's a V prime because so E prime, just we select any edge. So that's E prime. You take the endpoints of E prime, that becomes our V prime. Okay. So now this edge in E prime, we know that they do not share any end nodes. Right? So this is E prime, and V prime we just obtained from E prime. So so let me just say that we know that V prime is 2 times V prime is equal to E prime because E prime are independent. So these edges in E prime do not share endpoints. They are independent. So in other words, these edges is like this. They don't share any endpoints. So that's how I pick my E prime. So all these endpoints, you take them up, it becomes our V prime. Okay, so now let's see this. Okay, so these edges, so these are the edges. They must have, so these edges must have at least one point in V star. Oh, I call it C star, sorry. So now because C star covers all these edges, then these at least, so for any edge, at least one point is covered by C star. So that means we have C star is now at least one point is covered. So that means we have that the size of it. Okay, so each edge, at least one point is in it. So that means the size of E prime is, the size is above, is bounded above by the size of C star. But then we know we have this. Okay, so that we have, now we put this in, I call it C. So this is approximation value would be C here. So that is the size of V star. So then we have 2C. Okay. That's equal to the size of E prime, and that's less than this, equal to this. So that means now you get C star. Maybe I shouldn't use, maybe I can say C is just the size. So that would go better, but this is okay. So that means that C star, okay, you put C over, so from here, we get, so you get, sorry, I put this 2 wrong, right? So this 2 should be here, because each edge contributes 2 points in my cover. So that's this. So that means that I have, so E, now we know that each edge has at least one point in C star. So that means the number of edges should be bounded above by the number of nodes in my optimal cover, in the minimum cover. But then this E star is equal to C over 2. So that's my approximation. So then we have C over, so you put C stars, and then put 2 to the right. So that's bounded above by 2. Now this is always greater than or equal to 1. So that's how we get a ratio of 2. Now this looks pretty straightforward. So now let's just go back to see how can we come up with this? How can we make a connection with C, with the optimal solution? We don't know what it is, but then the approximation solution we constructed, we can use that to make connection to the optimal solution, because the approximation is a set of edges we constructed, and they are independent. So then because they are edges, they are covered by the optimal solution. Okay, so that is this. So that's how we did this. And then our approximation algorithm comes from this, the set of edges we selected. So that's how we make this connection, even though we don't know what C star is. But we do know this relation, okay? Because C star is a edge covered. It covers all the edges. In G, since E prime is a subset of edges, so it's covered by C star. So that's why we have this. Okay. So now let's move on to the next. Any question for me? Sometimes you need some twist of your thinking, to particularly when you try to make a connection of your approximation to your optimal solution. So that there is a one relation you need to get. Once you get that, it will be easier. And how do you come up with an approximation algorithm? Most likely it's a greedy algorithm. So in this case, my greedy choice would just be I pick any edge, okay, in the remaining graph. Once I pick it, I remove all the edges that are incident to this edge, and then I repeat this algorithm. Okay, so now let's look at traveling salesman problem, TSP. As I said earlier, so TSP is NP hard. Okay, so once again, let me say that problem again. So suppose you are given a undirected weighted complete graph. Okay, so I didn't mention complete graph earlier, but you suppose now your graph now is complete. Complete means that you have a connection between any pair of nodes, which means that Hamiltonian circuit always exists. Okay, so our earlier construction of binary search will still work on this case. So what we're going to find is a Hamiltonian circuit or cycle. Cycle means that your nodes don't repeat with the minimum total cost, okay, or total weight. And if your cost satisfies the triangle inequality, meaning, okay, so let's say I have a node U, V, W. So I connect this triangle. So this is a triangle because it's a complete graph. So any pair of nodes are connected. So they are connected. So let's look at the triangle. Then I'm going to see the cost of this edge. Now you think of it as a distance, right? So if the cost of this edge U and V is smaller or equal to the cost of UW plus the cost of VW, so this is V. Then we say that this cost function C satisfies triangle inequality. Okay, so if this cost is a distance, we know that it satisfies triangle inequality. Okay, but for the cost may not be. Okay, so for airline costs, the airline tickets, right? Sometimes the direct flights cost more than you go through other places. Okay, so for that problem, the cost does not satisfy triangle inequality. Okay, but now let's look at suppose this cost function satisfies triangle inequality. Then we have a polynomial time two approximation algorithm for solving TSP. All right, so what's the idea? Okay, so the proof looks here is a simple, but let me just open up a whiteboard to explain the idea. Okay. So now we have a connected graph. So this is a complete, not just connected, it's a complete graph, G. So we can find, now this is weighted. So the first thing we do is to find a minimum spanning tree of G. So this tree just looks like this. It may not be binary, but it just connects all the nodes. Okay, and then you add the weight on each edge, it's minimal. Okay, so that's minimum spanning tree. Sometimes we call it MST. But for some other applications, we may also need to find maximum spanning tree. That's also MST, right? So in this case, it's just minimum spanning tree. Now, once you have this, how do you form a Hamiltonian cycle? Okay, so this is how I do. So I start from the root, and then I'm going to go down. I'm going to do a pre-order traversal. So I first go in here, okay, and then I'm going to, so let's just do this, okay. We do a first order traversal, it's just like this. Each edge going up twice. All right, so this is how I'm going to do it. And then coming back. But then the problem here is that it is not a Hamiltonian cycle, although I go through every other node and coming back, but some of these nodes is being gone through twice, right? So for instance, for this node, you go here, here, now this node's once, but then you come back. Now, whenever I come back, I am going to make a node to connect this. So for this, I'm going to connect this node instead of going back. So for this, because the next one will be, sorry, not this one. Let me remove this. So this will be my tour. Now this is called a tour. But I want to convert this tour to a Hamiltonian cycle. So the way we do this is that when we need to backtrack, so this is a backtrack. So backtrack then, I'm going to connect this backtrack to this node. The next node, so the backtrack, you're going up and until the root goes to a new node, then you make that connection. Now remember, this backtrack edge, and then you go back. So so for this part, it's smaller than, so the cost of this new node you added is smaller than these two combined because of triangle inequality. So likewise, you come down here. Okay, so you go down. Okay, you backtrack again. So instead of going up, so now I'm going to make this connection. Okay, so now we get, sorry, not this connection, because you backtrack. Okay, so then you from here, you backtrack again. So now I don't go backtrack, instead I make this connection. Okay, from here you backtrack. So here you go like this, okay? You go here and you go here, you go there, you go backtrack, but this time there's no more edges left. So this backtrack just means you moving back, there is no other thing you can connect to, so you just connect directly to the starting point. So that means my Hamiltonian circuit is this. Okay. So now that's how I find a Hamiltonian circuit. Then I want to know the cos of this Hamiltonian circuit compared to the optimal one. Okay, so then we can use triangle inequality to prove the relationship of a approximation ratio of 2. Okay, now let's go back to the proof here. All right. Okay. So now we let H start. So this part is just what I explained earlier. So this part is what I explained earlier. So only a few lines, but then of course the idea behind this is what I said. Okay, now we let H star be a Hamiltonian cycle with minimum cost. We don't know what it is, but we know such things exists. Then since removing an edge from H star is a tree. So because it's a cycle, we take off any edge, it becomes a tree. So that means the cos of H star is at least greater than or equal to the cos of the minimum spanning tree, because you remove an edge from H star, then you have a tree, and the cos of that tree should not be smaller than the cos of a minimum spanning tree, but then you put an edge back. So that means that at least greater than or equal to this. So this is the first observation to make a connection of H star with the tree tour we constructed, because we started from a minimum spanning tree. Now, we know that for this cos of t, we multiply 2 because we remember we actually form when each node, when each edge is traversed twice, right? Remember the tree like this, right? So each edge, you go down, so you go back. So that means you look at each edge twice. So that means that I have that 2 times C of t. So each edge you consider twice, then you form a cycle, you're going back. Of course, this is a smaller, so H is the approximation algorithm we do. And this can be shown that it is using triangle inequality. So let me show that to you. Now, let's say we already showed this. Okay, then we have CH star greater than or equal to C of t, then this move this 2 over, stands greater than or equal to C of H2. So that means that we have a approximation ratio of 2. So now let's show this case. So why it is true. So why is this true? Using triangle inequality. So we just need to draw some lines, then you see it clearly. Okay. So let's say originally I'm going back here. So now I'm going to connect these things. So that means now you connect this line here, you connect this line here. I know this edge is smaller than, the cos of this edge is smaller than the cos of this edge plus the cos of that edge, right? So let me do it here. Start a clean. I do it once, do it here once, and when I come back, that's twice. I don't do this. Instead, I go into this node. So now you're going to see this. So this node, let's call this UVW. So the cos of UV, now this is the new edge I'm adding, than the original tour. So this is the cos smaller than or equal to cos of UW plus the cos of WV. So this is in the tour because this edge, you're going back, you backtrack. And this WV is not in the tour, but then you do it again. Because this edge, you're supposed to visit twice also. Now, we say that this edge is also, so this is CU and then CWV is smaller than, because you do this once, I'm sorry, twice now, is smaller than W, let's call it Z plus CZV. Okay, now this edge, you also do it twice. You only count it once. That means that this new edge I'm getting, instead of backtracking here, is so what we are getting is that if you think of all of these things, now because now I have this and that, each becomes the tree. So this is in the tree, this is in the tree, this is in the tree. So you replace this by this tree. So that means ultimately for any edge you add like this, you can come to the tree, so then they will be smaller than or equal to the second count of that edge. So that means ultimately you get 2 times C of t greater than or equal to C of h. Okay, so that's how you get it. It's the second time so the new edge you added will be just one time, right? So but the original edge you already counted, that's in your Hamiltonian circuit. But when you want to backtrack, you add a new edge. So that particular new edge, because of triangle inequality, will be less than or equal to the second count of the edge until you get down to that node. So that is the observation that we made, and that is also the proof that why this is the case. So once we have that, then we know that we have a approximation algorithm for TSP with an approximation ratio of 2. Okay. Now, what happened if triangle inequality is not satisfied? All right. How much time do I left? Okay, I only have 4 minutes left, so I'm just going to raise this question. So what happened? Okay, what happened if the cos function doesn't satisfy the triangle inequality? Then we have the following result. Suppose that P is not equal to NP, then for any constant R greater than or equal to 1, there is no polynomial time approximation algorithm with approximation ratio R for TSP. So that means that if the coarse function does not satisfy the triangle inequality, then we don't have any constant approximation. We don't have any approximation algorithm with constant ratio R for TSPs. So that means that any solution you can find there, then there is no constant approximation ratio, no matter how big that ratio is. So that's what we are going to look at. And I'm going to stop here because I only have 2 minutes left. So any question for me?
Not at this point.
Okay. Yeah, so we started a different direction. So our thinking is slightly different when we come up with an approximation algorithm. So the algorithm itself sometimes is not too complicated. It is more or less some greedy choice algorithm. So difficult part is the proven approximation ratio for this kind of work.
Have you looked at the recent TSP solution that made a slight improvement over the?
Yeah, I look at that. So that proof is much harder.
Yeah, I can imagine it's much harder. I haven't looked. I've just seen that it's there.
Yeah, that proof is much harder. It was more sophisticated proof. Yeah, but yeah. So normally people would like approximation ratio to be 1 plus epsilon, right? Epsilon is greater than 0, but they want to be that epsilon as small as possible. So that direction of work is highly mathematical. Play a lot of mathematical tricks. All right, then. So I will stop here and I will see you on Wednesday.
All right. Thank you very much.
Yep, thanks.
Thank you very much.
Yeah, bye-bye.